Good day everyone! Today I will be presenting about the half-wave rectifier signal. This presentation is part of our course on signals, spectra, and signal processing under the College of Engineering from Bicol State College of Applied Sciences and Technology. The focus of this presentation is to explain how a half-wave rectifier works from a signal perspective, covering its theory, mathematical representation, simulation, and actual implementation. This presentation is divided into four main parts. First, we will begin with an introduction to the half-wave rectifier signal. Second, we will discuss its mathematical expression, particularly using Fourier series representation. Third, we will analyze the system using a Simulink model. And finally, we will verify the concept using an actual hardware implementation. Moving forward, we have the half-wave rectifier signal, which is obtained when an AC input waveform is passed through a diode. The diode allows only one half cycle of the AC signal, usually the positive half cycle, to pass through, while the other half cycle is blocked. As a result, the output is no longer an alternating signal, but a pulsating direct current waveform. This slide also illustrates the comparison between the original AC input and the resulting half-wave rectified output, both in theory and in practical circuit setup. To better understand the half-wave rectifier signal in signal processing terms, we represent it using a Fourier series. Since the output waveform is periodic but non-sinusoidal, it can be expressed as a sum of DC and harmonic components. The first form shown is the trigonometric Fourier series, where the signal is expressed using sine and cosine terms. The second form is the exponential Fourier series, which represents the same signal using complex exponentials. And finally, the combined trigonometric Fourier series shows how the signal consists of a DC component, a fundamental frequency component, and multiple even harmonics components. These mathematical representations explain why the half-wave rectifier output contains ripple and harmonic distortions, which are important considerations in power electronics and signal processing. With this mathematical foundation, we can now relate the theoretical signal representation to simulation and real-world implementation, confirming how theory, modeling, and practice align. In this section, I will explain the working of a half-wave rectifier signal using a Simulink model. We will go through each block in the model, analyze the input and output waveforms, and finally, verify the theoretical operations through simulation results. This model is developed in MATLAB Simulink and represents a basic half-wave rectifier circuit. The purpose of the circuit is to convert an AC input voltage into a pulsating DC output using a diode and a resistive load. For the block 1, which is the AC voltage source, this block generates the input AC signal. It produces a sinusoidal waveform with a fixed amplitude and frequency, typically to 50 or 60 Hz. This waveform alternates between positive and negative values, representing an AC supply. Next, we have the diode, or the rectifying element. The diode is the most important block in this model. Its function is to allow a current to flow in one direction. When the input voltage is positive, the diode is forward biased and conducts. When the input voltage becomes negative, the diode is reverse biased and blocks the current. We also have the load resistor. This resistor represents the load connected at the output of the rectifier. The rectified voltage appears across the resistor. In practical system, this load could be any device that requires DC power. Next, the voltage measurement block. This block are used to sense the input and output voltages. These signals are sent to the scope for the waveform observation. Lastly, we have the scope block. This block displays the waveform. One channel shows the input AC waveform and the other shows the rectified output waveform. This allows us to visually compare the theory with simulation. Now we have the waveform of the Simulink model. Let us first observe the input waveform. The input is a pure sine wave, which both positive and negative half cycles. This confirms that the source is supplying an AC voltage. Comparing the two waveforms, clearly, The second waveform shows that the output is a half-wave rectified signal. The output is no longer alternating current but a pulsating DC waveform. This matches the expected behavior of a half-wave rectifier. According to the theory, a half-wave rectifier allows only one half of the AC cycle to pass. The average DC output voltage is lower than the input peak value. The simulation results confirm this behavior, exactly validating the theory. Using a measuring instrument such as oscilloscope, the input waveform is observed as a full sine wave. The output waveform across the resistor shows only the positive half cycles, while the negative cycles are completely eliminated. This output waveform exactly matches the theoretical half-wave rectifier waveform, the waveform obtained from the Simulink simulation. Now, in the final part of this experiment, we will verify the half-wave rectifier operation using an actual hardware on the breadboard. The components used and their functions are the following. The AC supplies provides the input signal. The diode performs rectification by allowing current only in one direction. The load resistor develops the output voltage. And finally, the oscilloscope is used to observe and verify the input and output waveforms. This breadboard circuit represents the practical implementation of the same half-wave rectifier that we simulated earlier. An AC input source is applied to the circuit using external signal leads. The diode is connected in series with the load resistor, exactly as shown in the theoretical circuit. The diode is oriented such that it conducts only during the positive half cycle of the AC input. The resistor acts as the load, and the output voltage is taken across the resistor. Now, when the input AC voltage is positive, the diode becomes forward bias. This allows current to flow through the diode and the load resistor, producing an output voltage. Now, when the input voltage becomes negative, the diode is reverse bias. In this condition, the diode blocks current flow and the output voltage drop nearly to zero. Thus, only positive half cycles of the input signal appear at the output, resulting in a half-wave rectified form. In conclusion, the half-wave rectifier was successfully studied using theory simulation and practical simulation. The Simulink model clearly demonstrated the rectification process, and the breadboard implementation verified the same behavior in real hardware. Both simulations and experimental results confirm that the diode conducts during the positive half cycle and blocks during the negative half cycle, producing a pulsating DC output. Thus, the objective of understanding and verifying the work of a half-wave rectifier has been successfully achieved. This is the end of this presentation. Thank you for listening.